For the next little bit of this, you are going to need your periodic table and then this sheet that says types of chemical bonds. Okay, the reason we need our periodic table to talk about types of chemical bonds is that when we start to look at what kind of chemical bond we're working with, the key to knowing what type it is the difference in electronegativity. We've learned that our periodic table tells us the electronegativity. It's just the dim little number. Electronegativity is the dim little number up here in the upper right-hand side of that box. So if we're going to calculate difference, it's nice to have all of our electronegativities given to us. We're going to take bonds and we're going to divide them into three separate categories. One category is going to be the nonpolar covalent. One category is going to be the polar covalent. And one category is going to be ionic. And I chose the blue, the green, and the yellow here because if you combine blue and yellow, you get green. And a polar covalent bond is going to have some traits of an ionic bond, some traits of a nonpolar covalent bond. And so that gets us kind of an intermediate situation. Up until this point in time, anytime you've encountered bonding, people have been there's covalent bonds, there's ionic bonds, that's it, that's the end of the story. But the truth is, bonding isn't such a black and white situation. It's more of a continuum of perfectly covalent bonds on one end of that continuum and perfectly ionic bonds on the other end of the continuum, and a lot of stuff in between that has characteristics of both covalent and ionic bonds. Remembering that your covalent bond is when you have a perfect sharing of electrons, and your ionic bond is when you've transferred the electron completely from one atom to the other, and you've created complete ions. But now we're going to tell you that there are some intermediate situations where, like, the electrons are being shared, but the sharing isn't exactly an equal sharing. Those shared electrons are shifted a little more toward one atom than the other. So this is another way to kind of look at the bonding thing, that our difference in electronegativity can be matched up with what we refer to as percent ionic character. And if that difference is very small, you're not going to have a very ionic bond at all. And the opposite of having an ionic bond is having a covalent bond. And the most perfect covalent bond is what we call a nonpolar covalent bond. And so anything in these kind of first three columns here with a difference of 0.1, 0.2, or 0.3, we're going to put into the category of nonpolar covalent bond. The electrons are being shared so equally that from the outside, we can't notice that one end of the bond is more negative than the other end of the bond. At the other end of the spectrum, once we hit 1.7, our bond is, for all practical purposes, more ionic than it is covalent. It's more of a transfer of electrons than it is a sharing of electrons. So that's this end of the continuum. But in between our perfectly covalent bond and our ionic bond is something that has some characteristics of both. It's got some characteristics of sharing, but it's got some characteristic of transferring electrons because the electrons aren't perfectly shared between the two. And that's this middle range right here. So starting with an electronegativity difference of 0.4 and going up until it gets to be about 1.7, we have bonds where the electrons are shared, but they're not shared equally. So we're going to look at the three possibilities here. Our first possibility is that we have an ionic bond. An ionic bond is actually very easy to recognize. You don't even have to do any calculating to figure out if you have an ionic bond, because an ionic bond is what you get when you have a metal and a nonmetal. That's always been the case. We aren't changing the rules at all. We're just going to give you a little bit of background in terms of why that ends up being an ionic bond. When you form an ionic bond, that bond is formed from elements that are very far apart on the periodic table. Something from the metals area, something from the nonmetals area, and because they're very far apart on the periodic table, their electronegativity difference is very big. The nonmetal has such greater pull on that electron that the nonmetal, for all practical purposes, removes the electron from the metal and takes it for itself. And the net result here, when a metal gets together with a nonmetal, you end up with a positive ion and a negative ion, and the two just stick together. And that's an ionic bond. This one, a positive ion is being attracted to a negative ion. And probably the classic example of that is table salt. Sodium is a positive ion. Chloride is a negative ion. And the two stick together just because positive and negative things are attracted to one another. So that's one end of the spectrum. The electron is essentially transferred from one atom to the other. The net result is that we have ions, and the bond itself is where those two ions stick together. At the other end of the spectrum, we have this nonpolar covalent bond. A nonpolar covalent bond represents an equal sharing of electrons. And this is what you get when the two atoms that are making the bond have the same or a very similar electronegativity. It's like tug of war between a set of twins. Everybody is equally strong, so the rope ends up staying exactly in the middle. A good example of this would be any of your diatomic elements. So like if two fluorines get together, the shared pair of electrons sits exactly in the middle between them because they have equal electronegativity and therefore an equal pull on those electrons. And we can get what appears to be an equal sharing of electrons even if the atoms aren't exactly identical to one another. If the atoms have a very similar electronegativity, any unequal sharing is not unequal enough that we can even tell that from the outside or in terms of the behavior of the bond. And it seems to be that the threshold for us to be able to notice polar characteristics in the bond is about 0.39. So if it's 0.39 or less, it's going to go in this category of nonpolar. When it hits 0.4 for a difference, we start to be able to see from the outside some characteristics of what's called a polar covalent bond. A polar covalent bond is sharing, but not sharing in an equal sort of way. This is the case where one element is more electronegative than the other, but not so much so that it can take the electrons all together, just enough that it can pull those shared electrons a little bit closer to itself. Good example of this one is the hydrogen-fluorine bond. Hydrogen has an electronegativity of 2.20, whereas fluorine has an electronegativity of very large, about 3.98. So fluorine has a much, much bigger hold on those electrons. So the electron cloud gets pulled in the direction of the fluorine, and the shared electrons are shared in such a way that fluorine has them more often. And it's just because fluorine is more electronegative. So they are still sharing because it's two nonmetals, but that sharing is relatively unequal. The net result of this unequal sharing is something called dipoles, or positive charges. It results in your bond having a positive end and a negative end. If we look again at our HF molecule, where the electrons were shifted in the direction of the fluorine, what we see from the outside is that the fluorine end of this bond is a little bit negative, and we use the lowercase Greek delta to say a little bit. It's not a total and complete -1 charge. It's just a little bit negative, and because the electrons moved away from the hydrogen, that end of the molecule is a little bit positive. And that's called a dipole. The other way you will sometimes see this represented is with the electrons back drawn as a bond, because they are, and then an arrow underneath that says the electron cloud is pulled in the direction of the fluorine because of fluorine's greater electronegativity. And then often they drop a little hash over the back end of the arrow. And that's sort of handy because if you cover up that much of it, it looks like a positive sign, and it reminds you that the positive charge is on the end away from where the electron cloud is being tugged. So look at a few examples here. On the back here, we have a little chart, and we're going to do 2 of them together, and then we'll turn you loose to work on the rest of them. So if we want to know about the bonds, the first thing we do is we look up the electronegativity for each of the elements involved here. So carbon has an electronegativity of 2.55, and chlorine has an electronegativity of 3.16. When you calculate the difference, you're just going to subtract in the direction that gives you a positive number, or just think of it in terms of taking the absolute value. Since these are 2 nonmetals, we can pretty much rule out the possibility that they're going to make an ionic bond. So we're more worried about whether this bond is going to be polar or not. We know that we have to have an electronegativity difference of at least 0.4 for it to be polar. 0.61 is well past the threshold. This is a polar covalent bond. And then anytime we have a polar covalent bond, we're going to draw the dipoles. So our bond is a carbon to chlorine bond. And with the chlorine being more electronegative than the carbon, the electron cloud is going to get pulled in the direction of the chlorine, leaving a positive at the carbon, or we can denote that with our partial negative and partial positive. And I don't have a preference how you choose to represent your dipoles, or if you like representing them both ways, that's just fine as well. Next one. Carbon has an electronegativity of 2.55. We already looked that up. Hydrogen has an electronegativity of 2.20. If we calculate the difference, we come up with 0.35. That doesn't cross our threshold value of 0.39. So this is nonpolar covalent. And because the electrons aren't shared unequally, we don't develop any dipoles. We don't have to do anything there at all. This bond doesn't have a positive end and a negative end because the electronegativities of the elements involved are too similar. So before we add anything to this, I want you and your partners to take some time, fill in this chart, and make sure you're good on understanding what type of bond you have in these different situations. So take a couple minutes to work on that.